Hello, this podcast is on frictional forces. We're going to take a look first at some key terms, then the standard friction model, followed by quantitative analysis of friction and quantitative analysis of drag forces. First, let's look at some key terms. A frictional force, it's a push force exerted between two surfaces that act parallel to these two surfaces. It can either impede or hinder motion. Friction is the frictional force between two solid surfaces. For example, car tires on a road. Its symbol is F sub F or just lowercase f. We typically will use the term friction if it's impeding the motion, and we often will use the word traction if it's aiding the motion. For instance, when you're accelerating in your car, this friction force between the tires and the road is what we would call traction, and when we're braking, trying to slow down, we would call it friction. But again, it technically is friction. Just wanted to make you aware of, sometimes we loosely give it a different name, friction or traction, depending on whether it's impeding or aiding the motion. Drag is the frictional force between a solid and a fluid, or between two fluids. For example, air resistance is a type of drag force. It's the resistance of the air molecules on the solid object moving through it. Keep in mind when we say fluid, that could be a gas or a liquid. Finally, the symbol for drag is F sub drag. And when it comes to friction, we have two types of friction: static friction, and that's the frictional force between two solid stationary surfaces. For example, a box sitting on the floor, and you'll see that symbol is F sub Fs, or often just F sub S, and that would be a lowercase f. The other condition is kinetic friction, and that's the frictional force between two solid sliding surfaces. Note, not rolling surfaces, but sliding surfaces, such as a box being pushed across the floor. Car tires rolling on the road would not be considered kinetic friction, because if you think about it, the tire and the road are not sliding past each other. So let's take a look at the standard friction model. And let me first say this is not a perfect model. Again, a model is just an explanation, but it handles most of what we would call our common situations when we have two surfaces, two solid surfaces in contact with each other. But there are some instances where it does not apply, but for our purposes in our course, we will use the standard friction model. And so in this case, we look at a microscopic view of the surface, and no matter how smooth the surface is, even if this were smooth concrete or ice, we would see peaks and valleys at the microscopic level. And this wooden crate, even if it were something like a smooth plastic crate, we would see peaks and valleys. And so when these two surfaces are in contact with each other, it creates this meshing of the peaks and valleys of the different surfaces. And you can see here how they kind of get interlocked. And then when you apply a force to the crate and you're trying to move it, what you get in these individual points is you get the floor surface, in this case the concrete, pushing against and opposing that motion. And we can just look at this little blow up, and we can see three different points on a microscopic level where the concrete peak would be pushing against the peak of the box's surface. And when you add up all these microscopic forces, it creates a noticeable and significant force that we call friction. This explains one of the main characteristics of friction, which we notice that as the roughness or stickiness of the two surfaces increases, the friction force increases. And of course, this observation fits nicely with this standard model explanation. We also know that because of gravity, we have the floor, in this case, pushing up and exerting a normal force on the moving surface, or the surface that would be attempted to move. So when you have these interlocking peaks and valleys, it makes sense that if you're pressing them together more tightly, stronger, and that's what the normal force is doing. It's pushing these peaks and valleys into each other. Well, it would stand to reason that the stronger the normal force, the stronger these friction forces would be. And indeed, we observe that as the normal force increases, the friction force increases. And then finally, we notice that when the object is stationary, the friction force is stronger than once it starts moving. And perhaps the best way to explain this observation is if we think of these interlocking peaks and valleys at the microscopic level. If the object's not moving, these peaks and valleys have a chance to settle into each other and really get firmly established. And that would create a stronger friction force. Whereas if the object is moving, then these peaks and valleys are moving past each other quickly and they don't have a chance to get as firmly entrenched, and then these microscopic friction forces are not as strong. Let's move on and talk about the quantitative analysis of friction. So we know that from observations, the frictional force is proportional to the normal force between the two surfaces, and it's also proportional to the roughness or stickiness of the two surfaces. And that leads us to our equation that the static friction is equal to the coefficient of static friction times the normal force, and similarly for kinetic friction, it is equal to the coefficient of kinetic friction times the normal force. And of course, the normal force is a measure of how tightly these two surfaces are being pushed together, and the coefficient of friction is a measure of the roughness or stickiness of the surface. For instance, an ice cube sliding on the road would have a much lower coefficient of friction than a rubber car tire sliding against a road. Again, the higher the coefficient, the rougher / stickier the connection is between the two surfaces. And that's another important thing. The coefficient of friction is for a specific pair of surfaces. So for instance, if you calculated the coefficient of friction for your car tire on dry pavement, that coefficient of friction isn't characteristic of the car tire, it's characteristic of the interface between the car tire and the dry road. Because indeed, if you were to measure and calculate the coefficient of friction on the same road when it was wet, you would find that that coefficient of friction would be much less than when the road's dry. Because again, the coefficient is a characteristic of the interface or interaction between the two surfaces. It's not dependent on just one of the surfaces. It is a function of both of the surfaces. Let's take a look at the friction force versus time graph and just try to understand this a little better. So we break it into the static region and the kinetic region. Let's say, for instance, we're pushing a box across a concrete floor and the box is initially at rest. The static region is the time when we're applying a force but the box isn't moving. The kinetic region is the time when we're applying the force and the box is moving. So if we were to measure our force and we would gradually start increasing the strength of our push force, we would notice that, of course, force would increase, but the box would remain stationary up until it reaches its maximum static friction. And that maximum is determined by the coefficient of static friction for the two surfaces multiplied by the normal force of the surface pushing up on the object you're trying to move. Then once we exceed that force, the box starts to move and we'll notice a quick drop off in the friction force, and then it'll level out again. And this, once you get past this transition period and you reach this level force, this is now the kinetic friction force, and it is equal to the coefficient of kinetic friction times the normal force. So an important thing to know is when you apply a force less than the maximum friction force, the friction force is only equal to the force you apply. In other words, if you push on the box with 50 newtons and this maximum static friction force is 100 newtons, the floor is not going to exert a friction force of 100 newtons if you're only pushing with 50 newtons. It is going to match the push force until it reaches its maximum and can't push any harder. In that way, it's much like the normal force. Because static friction is stronger than kinetic friction, it stands to reason that the coefficient of static friction is a larger number than the coefficient of kinetic friction. Let's move on and talk more about the normal force. There are different factors affecting the normal force. On a level surface, we know that the normal force is equal to and in the opposite direction of the force of gravity. This would mean that the normal force is equal to the weight of the object. And because we often look at horizontal surfaces, we tend to think that the normal force is equal to the weight of the object that's sitting on that surface, resting on that surface, but that's not always true. For instance, if we have a sloped surface, here the box is resting on a sloped surface, gravity is going straight down towards the center of the earth, and the normal force is perpendicular to the sloped surface. So they are not exactly opposite of each other, and what we have is the normal force is equal to the y component of the gravity force. So we have normal forces equal to and in the opposite direction of the y component of the gravity force, and that's the mass times g, which is 9.8 if we're on the surface of the Earth or close to the surface of the Earth, times the sine of theta sub g. And theta sub g is the angle of the gravity vector measured from the positive x-axis counterclockwise to the gravity vector. And the quick formula for coming up with theta for the gravity vector, it's going to be 270 degrees plus or minus the slope of your incline. And in this case, when the slope goes upwards left to right, you're subtracting the angle of the slope. If our incline had been sloped the other way, you would be adding the angle of the slope to the 270 degrees. However, there is another shortcut that might be easier for you to deal with. And if we let the angle of the slope equal phi, then the normal force is equal to the mass times the gravitational field strength times the cosine of phi. Now this equation is only dealing with the magnitudes of the forces. This is not giving you any directional signs. So the normal force is equal to mass times g times the cosine of the angle of the slope, which I'm calling phi. A word of caution here on the AP exam problems, they will use the symbol theta to mean the angle of the slope. So if you're given a problem and they say that theta is 30 degrees, they mean the slope is 30 degrees. They do not mean that the angle of the gravity vector is 30 degrees. Let's move on to one other situation where the normal force is not equal to the weight of the object. And that's when we have an external force that's not acting parallel to the surface. It will either increase or decrease the normal force compared to the weight of the object resting on the surface. So here we have an example. Let's just assume this is a box sitting on a surface and we're pulling it with a rope, and we're not pulling the rope horizontally, but we're pulling it up and to the right at some positive angle theta. Well, this creates a y component or a vertical component of this force, and that y component is going to act to reduce the normal force. On the other hand, if this force were going down and to the right with a negative angle theta, it would give us a vertical component that was pushing or pulling down on the object, and that would create an increase in the normal force compared to the object's weight. So again, in this instance, the normal force would be equal to the force of gravity less the strength of the y component force. And of course that would be equal to m times g, which is our weight, minus the strength of this non-parallel force times the sine theta. Again, a note here in this equation, all these forces in here are magnitudes only, no directional signs. This wraps up our discussion of friction, which is the frictional force between two solid surfaces. Let's move on to drag forces. The frictional force is a function of velocity. And as velocity increases, the drag force increases. So drag is not constant during accelerated motion. And the general formula for the drag force is that it's equal to K times V to the nth power. K is known as the proportionality constant, and of course V is the symbol for velocity. And sometimes it's linear and sometimes it's nonlinear. So for instance, air. At low speeds, an object falling through air will experience what we call linear drag. So the drag force is proportional to the velocity, where again K is a proportionality constant. However, if the object is falling through the air at high speeds, we notice that the relationship between velocity and drag force changes. We still have a proportionality constant that is based on the drag coefficient that has to do with the shape of the object, capital A, which is the cross-sectional area of the moving object, and rho, which is the density of the fluid, in this case the density of air. So the velocity term, though, at high speeds is not linear, it's quadratic. This means that at high speeds, the drag force increases at an even greater rate as the object gets faster. Well, let's take a look at terminal velocity. So terminal velocity is the constant velocity motion caused when the force of drag increases to equal the opposing force that is causing the motion. Now this can either be horizontal or vertically. We most often think of free fall, things falling, but it could also be a car speeding along a surface, or a missile or an airplane going through the air. So it's not always things falling. So this general condition, terminal velocity, is reached when the drag force is equal to the opposing force that's causing the motion. So let's take a look at the stages of free fall. In stage 1, the object was just released from an initial velocity of 0, so the drag force is 0, and therefore the net acceleration downward is equal to the acceleration caused by gravity. And here's our force diagram showing that. Then, because it's accelerating downward, as time goes on, the velocity increases. And of course, as the velocity increases, the drag force is going to increase, and that causes the net acceleration to decrease. Now notice I said the net acceleration. If we take a look at free body diagram number 2, which matches this situation, the gravity force does not change. The acceleration of gravity does not change. However, as the object goes faster and faster, this opposing drag force does get larger. That lowers the net force, which in turn lowers the acceleration. But the object is still getting faster. So as it gets faster and faster, the drag force gets larger and larger, and eventually the drag force equals the acceleration due to gravity. And when that happens, the net force vertically is 0, and we have no acceleration, so our gravity force and our drag force are balanced, and we have constant velocity. In this condition, we use the term terminal velocity. So let's take a look at how we would calculate this. And first, let's talk about the motion equations for linear drag. The net force equation and Newton's second law equation govern this motion. And if we take a look, the net force equation tells us for an object falling, the force of gravity plus the drag force is going to give us the net force. The force of gravity is m times g, and we know the drag force is k times v to the nth power. Then we can use Newton's second law. We're just going to rearrange it to have acceleration equal to the net force divided by m. And so when we divide m into our net force expression up here, it simplifies to the acceleration is equal to g plus the proportionality constant divided by the mass of the object times v to the nth power. Now, if we take a look for falling linear drag, the nth power is 1, and we're subtracting the velocity term. So that lets us know that the acceleration is equal to g minus k divided by m times the velocity. So to find terminal velocity, we can solve this equation for v when the acceleration is 0. So we just do this simple rearrangement, and the terminal velocity of an object is equal to g times the object's mass divided by the object's proportionality constant. Now let's take a look at how we get the velocity equation for linear drag. We have from the previous slide, we had our expression for acceleration, g minus k divided by m times v. Well, we know that acceleration is dv dt, the rate that velocity changes with respect to time. So this gives us a simple differential equation, which we need to go through our steps of solving. So we separate variables, we set up our integration from t equals 0 to t. We get this expression after we solve our integrals. We now need to algebraically rearrange this to solve for velocity, and we're left with this expression. Notice that this ratio, k divided by m, the proportionality constant divided by mass, pops up in both of these natural exponents. And so we give that the symbol tau, and it's just known as a characteristic time. M divided by k, we know that the terminal velocity is equal to g times mass divided by k. We found that out on the previous slide. So if we make these two substitutions into this equation, it just becomes a little simpler form in that the velocity is equal to the initial velocity times e to the negative t divided by tau, the characteristic time, plus v sub t times, in parentheses, 1 minus e to the negative t divided by tau power. This relationship is an inverse exponential relationship. And let's just take a look at what happens as time gets larger. This term goes to 0, and this term goes to 0, and that just leaves us with v sub t times 1. And that would make sense that as time goes on, the velocity eventually reaches the terminal velocity. Now let's take a look at what that looks like graphically. We just have a velocity versus time graph for an object falling. Its velocity will increase, and it will begin to level off as the drag force gets stronger and stronger, and as the drag force approaches the strength of the gravity force. This is an asymptote established at a velocity which we know as the terminal velocity. Here our time axis is just given not in terms of absolute time, but in terms of this characteristic time, tau. Remember, the characteristic time is k divided by m, the mass. And notice at 1 tau, the velocity is 63% of the terminal velocity. By the time you get to 4 times tau, you are essentially at, for all practical purposes, terminal velocity. We do consider an object reaching its terminal velocity in the case of linear drag at 4 times its characteristic time. Let's go on now and look at establishing an equation for position. We've done an equation for terminal velocity, we've done an equation for velocity. Let's do an equation for position. We take our velocity equation from the previous slide, and we know that velocity is dy dt, the change in vertical displacement with respect to time. Again, this gives us a simple differential equation. So we separate the variables and we integrate from t equals 0 to t equals t. And we're left with this expression, y minus y0. Now we can go ahead and make some collection of like terms here and get a little simpler version where y minus y sub naught is equal to v sub t times time plus v sub naught times tau times this exponential expression plus v sub t times tau times this exponential expression. We won't ever have to use this mathematically, but I think what's interesting is to look at the graph. Here's our position versus time for linear drag. Let's just remember that if we were falling in the absence of air resistance, we would have a fairly sharp or steep parabolic curve. Now this may look like a parabolic curve initially, but it's not. As you see, it is increasing exponentially, but it eventually straightens out. And that happens approximately at the time equal to 4 tau. And again, that's 4 times the proportionality constant divided by mass. At that point, your slope approximates the terminal velocity, and the velocity remains constant. That ends our discussion on drag forces and frictional forces in total. I hope you found this helpful. Have a good day.